Hi, our topic for today is Taylor polynomials and approximations. So let's define first the notion that we need. Here's the definition. Let f be a function which has first n derivatives. Pn of x defined where at point x equals c. Pn of x equals f of c plus f prime of c over 1 factorial x minus c second derivative at c2 factorial x minus c squared and so on, plus f nth derivative at c over n factorial x minus c to the n is called the nth degree Taylor polynomial of f centered at C. So C is the focus of our interest, or around which one everything is analyzed. In special case, when C is 0, then it has a special name. The same thing, the special case is Maclaurin polynomial. I will just use Taylor polynomial for all the cases. But generally, this is somewhat complicated formula, just long, but it's fairly easy to see what's happening here. So that polynomial part is here. So this is constant term. This is first power, second power, nth power. So we add up these monomials of powers with exponents all 0 up to n. And then those are coefficients. So coefficients basically use values of the derivatives of our function f at point c divided by some factorials. So, as I said, the formula looks long, but it shouldn't be complicated to calculate. And of course, the main thing is, why would we do that? So we'll see that in a little illustration in a minute ago, showing how important they are basically for approximating functions by polynomials, which makes it available, actually the process of estimating the values of the function accessible to calculators and computers. So this is basically the essential technique that our calculators use to calculate values of some differentiable functions. Well, let's first see how the process of calculating them goes. So here's example. Find 6th degree Taylor polynomial, I'll just write it, of f of x equals ln 1 plus x at x equals 0. So it's Maclaurin polynomial. So here's what we need to do. So how does the process work? We calculate the derivative functions and the derivatives. So f of x is ln of 1 plus x. And then what do? Calculate first derivative, which is 1 over 1 plus x. Then second derivative is, we use the quotient rule, or power rule with the chain rule, negative 1 over 1 plus x squared. It's actually maybe better if I write it negative 1 plus x to the negative 2. Why? Because then it's ready for the third derivative, where negative 2 comes down, we get positive 2 times 1 plus x to the negative 3. Then fourth derivative, then even 3 comes down, so we get 3 times 2, 1 plus x to the negative 4. Fifth derivative of x will be negative 4 times 3 times 2, actually plus 4. And that would give us 1 plus x to the negative 5. And then sixth derivative will give us what? Negative 5, 4, 3, 2, 1 plus x to the negative 6. So we calculated all 6 derivatives. And then we just plug in x equals 0 and all of that. So this will give us what? That f of 0 is ln of 1, which is 0. F prime of 0 is 1. F second derivative of 0 actually is just negative 1. Third derivative is 2. Fourth derivative, because the remaining part is just 1, it's negative 3 factorial. Fifth derivative is 4 factorial. Sixth derivative of 0 is negative 5 factorial. So that's it. We have all the coefficients, and we are ready to write our polynomial. So it's P6 of x, which is equal, value is 0, plus 1 over 1 factorial, which is 1, but just for kind of uniformity. So that will be times x. And then it will be minus for the second derivative, minus 1 over 2 factorial x squared plus, now it will be 2 over 3 factorial x cubed minus, this 2 you can think of it as 2 factorial, which is the same thing again for uniformity. Then it will be minus 3 factorial over 4 factorial x to the 4th plus 4 factorial over 5 factorial x to the 5th and minus 5 factorial over 6 factorial x to the 6th. So it is a really polynomial of 6 degree as we were looking for. And what would that be? Which is just x minus, this is 1/2 x squared. And then what happens here, and that will be a pattern in the future, because if you have 2 factorial over 3 factorial, that's just 2 factorial, and this one is 3 times 2 factorial, because it just starts one step earlier. Factorial cancel, and we get 1/3. So it will be 1/3 x cubed. And the same thing happens here. 3 factorial over 4 factorial, 3 factorial, all the numbers from 3 down. This is 4, and all the numbers from 3 down. When that cancels, you get 1, 4. And then you get an idea that will be plus 1/5 x to the 5 and minus 1/6 x to the 6. So that's it. So we just plugged in, calculated what they gave us in the formula, and we got our 6-degree Taylor polynomial, Maclaurin polynomial. Here at center that z equals 0 of 6 degree. So now the question is, so okay, so we can calculate it. So what's the purpose of calculating? And I hope that the next applet will actually show you why are we doing it and what's our goal here. Taylor polynomials are related to functions.
As we mentioned a minute ago, we can represent Taylor polynomials of particular functions using software. So here is what we can do. Here's a function f of x equals cosine x, and then we also have a red, which is a green graph, and then we have a dotted red line, which represents a straight line. Why? Because that's polynomial of degree 0. So if you want just constant polynomial, the best approximation around x equals 0 would be just horizontal straight line. Then if we want n to be 2, n equals 1, nothing changed, but then n equals 2, we get the parabola. And if you look at this parabola and cosine x function have different nature, but you see how well they agree between -1 and 1. So between -1 and 1, even just quadratic polynomial does a pretty good approximation. And then after that, they really start diverging from each other. But let's look at the 4-degree polynomial. Then 4-degree polynomial approximates our cosine x for a longer time. So now it's pretty good between -2 and 2. So the higher we go with the polynomial, the better the approximation is. That means with that degree, it really approximates our function for along a much longer interval. So here it is n equals 6. Now it's even between negative, all this n equals 8, n equals 10. And that one already covers it between -4 and 4. If I do n equals 11, nothing will change, because if you remember, our Taylor polynomial only has even numbers for cosine x, because cosine x is even function, and you can see here that's 10-degree polynomial. And then if we go all the way to 20, the degree 24, here is that very long polynomial. But look how good this approximation is. Actually, it approximates our polynomial, our function, quite well between -9 and 9. And of course, we will see in section 9.10, if you go all the way to infinity, that means if you take infinite series, then it will approximate it between -infinity and infinity.
So you saw from our exploration that Taylor polynomial sometimes really very nicely approximates our function. So even in that example of cosine x and polynomial, you know that at the end they cannot be the same thing, because polynomial at the end goes to infinities and cosine always oscillates between the values. But you also saw the higher degree we use, our polynomial approximates function for a longer and longer interval. And actually that's the main idea, how calculators approximate differentiable functions, just approximate them with their Taylor polynomials. And then of course the dilemma is always how far to go to the degree, because higher degree means more calculation, but generally they actually estimate how many members are needed to make an error smaller than the assigned one, which is usually accurately to 10 digits. So that's how they wrote the program there, and actually what they did, they used the theorem that I want to mention now. And also you notice in that example on ln of 1 plus x, that actually in that case, however high the degree was, we were not able to dramatically increase the interval of accuracy. So sometimes you can really go far, and sometimes we are limited and we cannot do more than a certain interval. And I hope that that all is explained in this theorem, theorem 919, Taylor's theorem. So theorem says, if f is a function differentiable through n plus first derivative. So this time we need one more derivative, and you will see in a moment why. On an interval containing C, then for each x in this interval, there exists z in the same interval. Actually, they specify that is between x and c such that f of x equals f prime c, f of c plus f prime of c over 1 factorial x minus c, which is just a polynomial, and use nth derivative of c over n factorial x minus c to the n. So that's our Taylor polynomial, the same one that we have above there. And here is that extra, so that's where actually is the difference caught. We use n plus first derivative over n plus 1 factorial x minus c to the n plus 1. So it looks exactly the same, but it's not calculated at c. It is calculated at that point z. So generally what happens is, if we draw this, so if we have c's here, and here is that interval, then if I estimate my function at x, then that z is, and we don't know where, we cannot calculate it, that's the ambiguous part, is somewhere in between. So it's not calculated at c like everybody else, it's somewhere between c and x. So that's the Taylor's theorem. Generally, the shorter way to write it is, because this is Taylor polynomial, this is Tn of x, and this is called Rn of x, like a remainder after cutting n members. So generally this formula says f of x is equal to its Taylor polynomial plus this term here that catches actually the discrepancy by how much they disagree. And then what? Obviously, and that's one of the main things for today, it will be that this Rn of x, so this member is very important to memorize. So it's not like the others, but just at the point z, this member will be used to estimate how much are we off using Tn of x with respect to f of x. So that's actually where our error is. And sometimes that error could be made really small, wherever you want. Sometimes it could be made small just if we are fairly close to the point c. So that's where different functions have different behavior. And generally, let's play with it, and that's the main thing that we need to learn today. So data analysis, now calculation is less important. Here is data analysis. So here it is. Example. Here is the theory. Example. Approximate ln of 105 using fourth degree Taylor polynomial and estimate the error. We are fairly, so what is this basically? What we want is the following. First, we want to see how much is our C. So generally, we remember from a minute ago, we remember the following, that ln of 1 plus x, that one was at c equals 0 obtained. Ln of 1 plus x was what? X minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. We did it all the way to 6. Now we cut it off at 4. That's what they say, 4th degree polynomial. And then what? Plus r4 of x. That's where our error is. And then what? Is this a good choice? Because this is the choice. This series is centered at 0. X, is around 0. And of course there is this 1. So generally we are calculating something. So x is close. If x is close to 0, then ln of 1 plus x is close to ln 1, which is exactly what we want. Because for Taylor polynomial, very often you are thinking about a nice point that's close to you, so that if that difference is small, your chances are much better to kind of minimize this remainder. So definitely, if I want to estimate ln of 105, then I say the following. I say ln of 105 is approximately, it's not equal. So obviously, to get this out of this expression, I should put x to be 0.05. So x is 0.05. And when I plug it in, I get ln of 105 is 0.05 minus 0.05 squared over 2 plus 0.05 cubed over 3 minus 0.05 fourth over 4, and that's approximately, if you put it in calculator, you will get something around 0.048790142. Usually I tell you don't provide too many decimals, but here it is important to see more decimals because we want to see how accurate we are. So here it is. All right. So so someone's asking us how much is ln 105. We are offering him this, and of course we know that that's not the exact result, but we're going to see how accurate is our estimate. So what are we going to do? We can estimate our error by calculating R4 at 0.05. So we remember how R4 looks like. It will be what? F5th derivative at some point z, that z is between 0 and 0.05, over 5 factorial. Here we would have, I better write it here, of x, and then I'll plug it in. So x, and here it would be what? X to the 5th. When z is somewhere between 0 and 4x. So that's what the formula says. So what we want is R4 of 0.05. 0.05, because we are 0.05 from 1. So we plug it in, x to be 0.05. And then what would that give us? R4 of 0.05 would be 5 factorial here. That's good because it makes it very small. And this is perfect. 0.05 to the 5th. This is very small number, so it's very promising. The only danger is that 5th derivative might be too high, and then we might be in trouble. If you remember from a minute ago, what were the derivative we actually had, 5th derivative, so I'll just copy from here, so we don't want to calculate all the way to the 5th derivative, so it would be what? 5th derivative was positive, 5th derivative of x, but we needed it at z, so 5th derivative at z equals 24 times 1 plus z to the negative 5. So that's what it is. So here we'll get 24 over 1 plus z to the 5th. And that would be 24 is 4 factorial, and 5 factorial as usually cancel out. So we get 1 over 1 plus z to the 5th times 5. And then 0.05 to the 5. And then what? Now is the problem, how to estimate this. We don't know where z is. It might be at 0, so generally here is the specific picture here. 0 is here, 0.05 is the value of x that we use, z is somewhere here. So what do we do here? We use what I would call the worst case scenario. So we don't know where z is, but what is the worst for us? Worst means what would make this expression the highest? And then what? 1 over 1 plus z to the 5th, and that's the only ambiguous part. This is a decreasing function. Why? Because the bigger z is, the bigger the denominator, so that function goes down. So generally what? The highest that 1 over 1 plus z to the 5th will be this part. That is in the beginning. So generally we can say that this is less than or equal 1 over 1 plus 0 to the 5th times 5 times 0, 0, 5 to the 5th. Here it is. So we can guarantee that our error is less than this. This was fairly simple because function was decreasing. What if function is more complicated? You can just put it in a calculator on this interval and then see what is the highest value of that quotient, and that value then is the bound on our error. So here it is. We can guarantee now that our error, which is what? Which is equal to what is this? 1 over 5 times 20 to the 5th. Because this is 1 over 20 to the 5th and 5 here. And when you divide this, what do we get? We get 625 times 10 to the minus 8. So what is that telling us? It's telling us actually that error can show up. This is 8 digit after the decimal. So 1, 2, 3, 4, 5, 6, 7, 8. So the most so our error could be here at most at the 6. So what can we guarantee for sure? We can say the following, that our result is for sure accurate all the way to the here up to the, so this is 1, 2, 3, 4, 5, 6, and then on a 7th decimal, because of this 625, it might be here 2 or 3 actually, since the new coming member is the last one is next one would be positive, so by cutting it off we did underestimate, so result might be a little bigger here. So if we add 6 times, then this might be 1 or 2. So we cannot guarantee this digit 1, 2, 3, 4, 5, 6, 7 because of the influence of the 8th digit, but we guarantee that that result is there. And then let me take actually the calculator and see what will calculator say. And basically calculator used the same strategy, they just went maybe with an extra member. So if we take a calculator and then do ln of 1.05, we'll get the following result. Let me see. We would get the following result. So calculator, that's 0.04879, 0.048. Make it next about each other so that you can compare 0.04879, 0.1642. Exactly, actually, it shows up that we were accurate all the way to the 8th digit. So if you keep it on, if you cut it off at 7 digits, we actually give ambiguity there, because if you round it, 7 digit will become 2, as we mentioned. No, it would become 1. So 901,642. So yeah, 901. So this is the same. And then, as I said, 0, we had 0, and they had 6, which is also compliant with what we calculate. So I hope that this example really illustrates what is done with the calculator. Actually, as I said, the only thing that they did, they didn't take 4 members, they took 6 members, and then they got all 10 digits accurate. And I hope that this illustrates why is this such an important topic for all the practical calculation. So this is the real essence of what we are studying in this chapter 9. This is much more important than anything we saw before. And now nothing really, just playing with this and the estimate of the error. So basically this section is already on the board. So a few more examples. So here it is, example number 52. Estimate. This is a little trickier. E to the 0.3 with the error less than 0.001. So here's the problem here is that they didn't tell us how many members to take. And that's really what calculators do. So they just told us what is the error that they will tolerate. So we have, it's the other way around. A minute ago they told us how many members and we estimated the error. Now they said, no, you choose how many members as long as you provide the error less than what's there. So here it is, a solution. If you do e to the x, so f of x is e to the x, all the derivatives are the same. So here it's really not problematic. So all the derivatives are e to the x. So when we plug in x equals 0, why? Because our input is 0.3, fairly close to 0, and 0 is good for calculation. So all these derivatives will give us 1. So generally, how does the polynomial look like? Pn of x, the polynomial, looks like this. 1 plus 1 over 1 factorial x, 1 over 2 factorial x squared, plus 1 over n factorial x to the n. I said it, but maybe I didn't emphasize it enough. We are doing Maclaurin C at around c equals 0. So here it is, I stopped at n, but I don't know how much n to take. So generally, if what I'll show you bothers you, here's what you can do. You can just do trial and error. Try n equals 3, n equals 4, and then see if you are getting close where you need. That's it. If you take more members than necessary, that shouldn't be a problem. Although for programmers, that's important because you are paying more in calculation. But doesn't matter, as long as you get the main idea, I'll be perfectly happy. It means you will get the perfect credit. So generally what's my error? So my error is Rn of x equals, it would be, so fn plus 1 fz over n plus 1 factorial, and then x to the n plus 1. So here it is. So Rn of 0.3 will be n plus 1 factorial here. All the derivatives are e to the x. When I plug in z, it will be e to the z, x 0.3, 0.3 to the n plus 1. So generally, things look really good for us. Why? Because look, this is 0.3, 1/3. The more you go, that gets smaller. Factorial gets smaller quite quickly. So generally, you know, in 3, 4, 5 members it will be for sure good, because what? If I put 5, I get 6 factorial, which is 720, or this guy will get it, and this guy also. As long as this guy doesn't make too many troubles, but that should be okay. Why? Because here it is. So the picture says we are doing things at 0. Our x is 0.3. We don't know where that z is. That's ambiguous. Z is somewhere here. But then we know e to the z is increasing function. Goes like this. So the worst case scenario, the one that will maximize our error, will be at the end. So this is for sure less than or equal. E to the 0.3 or n plus 1 factorial times 0.3 to the n plus 1. Here it is. And then e to the 0.3 is less than or equal to, you can see that. So generally that's less than or equal to 2 over n plus 1 factorial, 0.3 to the n plus 1. So how much n do I need to put there? I'll just go trial and error. That's the easiest thing to do. So what would that be? Let me try n equals 2. So I just take quadratic polynomial. Would that be good enough? That would give, I hope not, so that I show you that, you know, we are not always lucky. 2 over 3 factorial times 0.3. So what would that give me? It's 2 over 6 times 3 over 1,000. Ooh, we just got it right with the quadratic, which is 1 over 1,000. So generally what? I can say here what? If it's less, mine is just less than or equal. Probably I'm not that unlucky, that's exactly at 0.3. So 2 is for sure good, and you can see that, but just to be on the safe side, I'll do P3. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then when you plug in x equals 0.3, what are we gonna get? I don't know if I have that calculated. Yes, I do. So the result that we have is what? 1.3495. If we put it as calculator, so it will be e to the 0.3. The result would be calculator 1.34985 and so on. So here it is. Our error is 5 over 10,000, which is less. So error is so here is 0, here is almost 6. So error is approximately 0.0006 if you do more decimal, because here is 8. Then we have 0, 0, 0. So this is 0.06, but that's for sure less than 0.001. So it's, so you see, we were not much better than what they asked, so it's good maybe that we took third number. That's it. So generally there isn't much. Their problem related, again, another practice, estimate now, they do the same thing. For the problem that we saw on that GeoGebra illustration or applet, estimate cosine of 0.1 with the error less than 0.001, the same thing. So what we do is what? For cosine, how does it go? F of x is cosine x, f prime of x is negative sine x, f second derivative is negative cosine x, and third derivative of x is sine x. And then fourth derivative cosine x and so on. So what happens here, you can see quite easily that we have a pattern that repeats after every 4 derivatives, and that would be cosine, negative cosine, sine, and so on, and then it keeps going. So generally when x is 0, when we plug it in, because we'll again estimate around c equals 0, what will happen, and by the way, this is worth memorizing, because very soon in one of the coming sessions we'll actually need to memorize these Taylor polynomials or their approximate Taylor series that we'll mention later. So when cosine of 0 is 1, sine is 0, this is negative 1, 0, 1, and so on. So generally the value of the derivatives alternates. All the odd derivatives are zeros, and even derivatives are alternate 1, negative 1. So generally we have the following, that f of x equals f of 0, which is 1 minus 1 over 2 factorial x squared plus 1 over f of factorial x to the 4th minus 1 over 6 factorial x to the 6th and so on. By the way, what's interesting, which powers showed up? Just even ones. But if you remember, cosine x is even function, and that's exactly the reason why actually odd members had to disappear and even one showed up. So it reflects the nature of the function. So, plus, let me stop. So f of x is approximately, and let me do the polynomial. So that would be, how do you write the last member? So it would be what? X to the 2n, because that's 2nth member, because I just write the even ones. And then what happens? It would be 2n factorial. And then coefficient is what? If your n is even, it's minus. If n is even, that's 2 times. This is 2 times 2, 2 times 3. So this is n 2, 3. It's, if it's 2, it's plus. If it's 3, it's minus. So it's minus 1 to the end. So for example, you just tested this. If n is 1, that will give you negative x squared, as it should be, and so on. So what do we do now? What is the error? R 2n equals, what would that be? It will be x to the 2n plus 1 factorial formula says. And then what do we do? Here we have x to the 2n plus 1, and then here is 2n plus first derivative. That's 2n plus first derivative, like all other odd derivatives, it will be sine. Plus or minus, it doesn't really matter. But what we can say is the following: the absolute value of R2n is less than or equal whatever z is. So since this is absolute value of sine z over 2n plus 1 factorial x to the, how much is our x? We are using x to be what? 0.1. So use x 0.1, so 0.1. Here it is. And then here is even easier than before. I don't even care if it's increasing or decreasing. Sine z is less than or equal 1. So it will be less than or equal. So this is for sure less than or equal 1. Less than or equal 1 over 2n plus 1 factorial times 10 to the 2n plus 1. Because 1/10 is 10. Now we see how fast is this in its convergence. So and you saw from that applet, actually, even when we were far from the center of the series, we saw very nice convergence quite quickly. So this one is really fairly close, so convergence will be dramatic. So what actually the funny thing is that here it's enough n equals 1. Why? Because then R2, so if we take quadratic, R2 is less than or equal 1 over what? 2n plus 1 would be 3 factorial times 10 cubed. So that will be what? 1/6 times 100,000. So it's actually, our error is 6 times less than what we were allowed. So what do we say? So here it is. Let's say that f of 0.1. I better write it nicer. So what? Cosine of 0.1, which is our f of 0.1, is close to P2. I can recall, yes, P2, 0.1. We call it P2 because it's second degree, although we use n equals 1 because of those double indexes. So P2 of 0.1 would be what? 1 minus 2 factorial over 0.1 squared. So what would that be? This is 1 over 200. So 1 minus 0.005, and our value is 0.995. So that's what we suggest for cosine 0.21. Let's see calculator just to be on the safe side. So cosine, let me see my mode. My mode is degrees, that was bad. Remember in calculus we always use radians. So I'll go cosine 0.1, and here is the result. They got so calculator gives a 0.995004165. So generally our error is much smaller than what we were allowed, actually, because we also have report 00 here if you don't report anything. So it's like 4 over a million is our error, so 1,000 times better than what we were allowed. All right, so things really worked very nicely. So I would say that this section is fairly simple, so just memorize the formula, memorize it properly with Rn. That business with Z is a little tricky, but generally, as I said, since we don't know how much Z is, our main goal is to estimate it so that we are sure that that value does not exceed what we need. So in this case, we just said, oh, sine always stays between -1 and 1, which is good enough for us. Or in the other cases, we just called worst case scenario. So we looked at the graph on that interval and then picked the point that's worst for us. That means that maximizes the possibility of the error. And basically that's what we have here. Let me give you the hint actually and explain how comes that suddenly we started to study polynomials in the middle of studying series. So what will happen, and that's actually next 3 sections, now this n will start going to infinity. So instead of cutting it off, we'll just take infinitely many members. How that works we will see. And generally in that case we won't have approximate, we'll have equal. So we'll have series that equals our function. Basically it's the same thing because these Taylor polynomials are those finite sums of that series, but this is really the crucial section that will help us to also get the other notion when we have series. So this is Taylor polynomial, that means you just stop at certain degrees, so this is just polynomial.